Let us talk about the energy of in case of hydrogen or hydrogen-like atom. We are about to talk about the energy of the nth orbit. For this, you again consider the nucleus, which is having a charge Ze, and you have electron, which is having a charge negative E. This electron is essentially moving with some speed v, and it has some mass m, and the separation between this nucleus and this orbit is r. Now, if you look at the first postulate, then that was Ze square by 4 pi epsilon naught r square, that was equal to mv square by r. That will be used in describing the energy. Right now, you see, the kinetic energy, which I am denoting by Ke, that can be written as half mv square, isn't it? जो नॉर्मल हमारी एक्सप्रेशन किसी भी एक मास पार्टिकल की काइनेटिक एनर्जी की होती है, that I have written as half mv square. And as you had said that the first postulate says that Ze square upon 4 pi epsilon naught r square, this is equal to mv square by r. So from here you can take out the value of mv square. For example, यहाँ पे एक r जो है इस r square के एक r को कैंसिल करेगा, एंड अगर आप mv square की वैल्यू यहाँ से यहाँ सब्स्टिट्यूट करेंगे, then you see the expression for kinetic energy, you can get Ze square upon 8 pi epsilon naught r. This is the kind of expression you will be getting so long as this kinetic energy is concerned. This is a one type of energy you have talked about, isn't it? Now if you talk about the potential energy, then you must see that there is one positive charge and there is another negative charge separated by distance r. So essentially you are having the expression q1 q2 upon 4 pi epsilon naught r involved in this particular situation. If you use the expression q1 q2 upon 4 pi epsilon naught r, and for q1 you are substituting Ze, and for q2 you are substituting minus E, then you will be having the expression for potential energy as minus Ze square upon 4 pi epsilon naught r. You can see kinetic energy, potential energy, they are magnitude wise inversely proportional to r, because in a lot of questions you are asked things like that. So potential energy, once you have expressed this way, then you can write down the expression for total energy. Now if you talk about total energy, then this is the sum of kinetic energy and potential energy. And if you do that, if you sum these two, then you will be getting minus Ze square by 8 pi epsilon naught r. You understand? This is the kind of expression you are having for total energy. And essentially this is the total energy we are expected to talk about. किसी भी nth orbit की expression ये है. Before I move ahead, first you try to correlate ये तीनों energy जो आपने लिखी हैं, पहले तो इनकी correlation भी देखिए. The very famous relation you are getting from this place. You can compare the total energy and kinetic energy. You can see they are just reverse of each other. Total energy is negative of kinetic energy, you can see from this place. And if you talk about potential energy, it is double of total energy. Potential energy is twice of total energy. You understand? This is the kind of expression you will be having. Potential energy is twice of total energy. Total energy is negative of kinetic energy, and that way you can correlate potential energy and kinetic energy as well. कभी कभी हम क्वेश्चन पूछते हैं कि अगर पोटेंशियल एनर्जी x है तो काइनेटिक एनर्जी कितनी है, and believe me, this is a similar kind of expression you had when you talked about the satellite motion. Satellite motion के केस में भी total energy, kinetic energy and potential energy के बीच का relation यही हमारा rule follow करता है, and this kind of rule will be followed in those all situations in which force will be inverse square law following. In the sense, force अगर 1 by r square की proportional होगा तो ये relation आएगा ही. Here, in case of Coulombic attraction, you have force proportional to 1 by r square. In case of gravitation also, the force is proportional to 1 by r square. So this kind of relation is expected to get. Now moving ahead with that, now let us concentrate on this particular expression. अगर radius की expression r is equal to epsilon naught h square n square by pi m z e square, अगर आप उस रेडियस के एक्सप्रेशन में सब्स्टिट्यूट करेंगे, then you will be getting the total value of energy of the nth orbit. So let us write it down. So here, if you are writing down the energy of the nth orbit, then you are writing it as minus z e square by 8 pi epsilon naught r, and here at the place of this r, you are writing, say, epsilon naught h square n square by pi m e square z. This is the expression of r you have substituted from your earlier derivation of radius of the nth orbit. Then you see some of the things getting cancelled out. Here you can get energy of the nth orbit as minus, this pi is cancelling out, m e square going in the numerator, and in denominator you have 8 epsilon naught square, this h square is here, and n square. Now again you can see here I have kept some of the things constant जो कि हमने यहाँ रखी है, and rest of the things z square and n square अगर हमने उसको बाहर रखा है, तो this will be helping you in finding out the value of any of the energy levels, in the sense that the values in the bracket you have constant. If you substitute these values, m is mass of electron, e is electronic charge, epsilon naught is the permittivity of vacuum, and h is Planck's constant, then this value will be essentially coming into joule. But in case you convert into electron volts, then you can have minus 13.6 z square by n square electron volt. You understand? Energy of nth orbit will be written as minus 13.6 z square by n square electron volt, and that helps you in finding out the energy value of any of the orbits for hydrogen or hydrogen like atoms. n की वैल्यू यहां सब्स्टिट्यूट होगी, एंड एज यू हैड डन फॉर रेडियस, अगर आप हीलियम प्लस के लिए एनर्जी की वैल्यू सब्स्टिट्यूट करना चाहते हैं तो z की वैल्यू 2, lithium double plus के लिए z की वैल्यू 3, and so on. You will be substituting and getting the energy values. Now once you have got the expression of this energy, let us talk about the energy values so long as hydrogen atom is concerned. For hydrogen atom, if you are taking n is equal to 1 here, maybe n is equal to 2 here, and say n is equal to infinity, that is the last orbit. So in between somewhere you will have n is equal to 3, n is equal to 4, and so on. You understand? If you write down the energy values, then substituting in the energy equation, you have here minus 13.6 electron volt. The next n is equal to 2 will be having the energy, if you divide it by 4, that will be minus 3.4 electron volt. If you divide this expression by 9, then you will have the energy for the third orbit, that is minus 1.51 electron volt. Then for n is equal to 4, you will have to divide it by 4 square, because in this expression you have n square at the denominator. So agar n की value 4 है, तो 4 square, that is 16, will be dividing this minus 13.6. That will be approximately minus 0.85 electron volt, and at the end you have zero energy. This is the way energy is growing up. This picture you must understand. Here you have nucleus, उसका इलेक्ट्रॉन की फर्स्ट ऑर्बिट है, फिर इलेक्ट्रॉन की सेकेंड, थर्ड, फोर्थ. दिस इज द वे ऑर्बिट्स हैव गॉन. नाउ बेस्ड ऑन दैट, अगर आप इसकी एक स्पेक्ट्रा जैसी चीज पे डिस्कस करते हैं, तो let's suppose there is a tube containing hydrogen atom and it has been pumped by some energy, then all these electrons happen to jump to upper levels, and once these electrons start falling down, then all those group of transitions which are reaching up to n is equal to 1, that is called Lyman series, which falls in ultraviolet region. The first line is alpha line, second line is beta line, third line is gamma line, and so on. In case the electrons are rising up to higher level and say these electrons are coming back up to level 2, then this kind of grouping is called Balmer series, which falls into visible region. There again you have alpha line, beta line, gamma line, and so on. In case the electrons are falling up to say n is equal to 3, then you have Paschen series, then bracket series, then Fund series, but all of them will be into infrared region. Understand? जो यहाँ पे ज़्यादा lines हैं, you have to remember that larger the lines, larger is the frequency involved with that particular transition, and उसकी wavelength उतनी ही कम होगी. Lyman series ultraviolet region में है, Balmer series visible में है, and Paschen bracket Fund ये सारे infrared region में है. If you talk about the third postulates, then we can surely calculate the wavelength involved whenever such transition is taking place. So if I am talking about that, then for describing the various spectra, you should talk in terms of Rydberg's formula, which will essentially be using the third postulate, that was E1 minus E2. This is equal to Hc by lambda. Now you have already derived the expression for E1 and E2, that is say minus 13.6 Z square by n square. So here if you do the manipulation, then you will be getting some constant Z square into 1 by n1 square minus 1 by n2 square. And this is essentially the Rydberg's formula, which is used in describing the hydrogen spectra. Here R is Rydberg constant, and Z is the atomic number. Now N1, N2 is basically the initial and final orbits you can have. It can be the other way around. It all depends what kind of transition you have. The only thing is N1 should have a smaller value, N2 should have larger value. Now let's suppose you are talking about Lyman series. Then for Lyman series, let's suppose I talk about Lyman series. Then remember that this N1 will be equal to 1 and the value of N2 will be anything between 2, 3 up to infinity. Let's suppose in Lyman series also I am interested in getting the value of wavelength of alpha line. That means it is jumping from 2 to 1. If you are interested in calculating the wavelength for beta line, then it is jumping from 3 to 1, and so on. You understand? In case you want to apply this equation for Balmer series, then for Balmer series the value of N1 will be 2, because here you can see in Balmer series final transition is up to n is equal to 2. So here the value of N1 will be 2 and N2 can have any value 3, 4, 5 and infinity. This is the way it is. And जैसे जैसे आप ये value substitute करेंगे, lambda की value ज़्यादा होती जाएगी, and then you will see from ultraviolet it is moving on to visible, then it is moving on to infrared and so on. So this is the formula utilized so long as the description of the spectra is concerned. Now, once you have understood this concept of spectra, let us solve some of the questions based on hydrogen spectra. Imagine a situation in which a hydrogen gas tube has been pumped with .1 electron volt energy. अंडरस्टैंड? एक हाइड्रोजन गैस की ट्यूब है, उसको आपने 12.1 इलेक्ट्रॉन वोल्ट एनर्जी से पंप किया है. नेचुरली ऑल दीज इलेक्ट्रॉन्स विल बी जंपिंग ऑन टू हायर ऑर्बिट्स, कोई 2 कोई 3 मे बी हायर, कहीं तक वो इलेक्ट्रॉन्स जाएंगे. नाउ दे विल बी फॉलिंग डाउन. इन द प्रोसेस ऑफ फॉलिंग डाउन एक एमिशन स्पेक्ट्रा बनेगी. सो यू हैव टू फाइंड आउट द number of lines in the emission spectra. Find out the number of lines in the emission spectra. You understand? This is the kind of question we are asking you. Now you see, in this kind of question, for the first thing you have to do is try to see what is the minimum energy of the electrons existing in hydrogen atom. And that is, you happen to say minus 13.6 electron volt. Ground state में जो electron की energy है, that is minus 13.6 electron volt. And you are pumping an energy of 12.1 into this. So this is 12.1 electron volt again. So the maximum energy these electrons can have, that is equal to minus 1.50 electron volt. Understand? जो electron के पास energy maximum आएगी, that is equal to minus 1.50 electron volt, and try to see the kind of picture you can have so long as the jumping of all these electrons is concerned. You had said that for n is equal to 1, the value is minus 13.6 electron volt. For n is equal to 2, this value happens to be minus 3.4 electron volt. For n is equal to 3, it is minus 1.51. For n is equal to 4, this value was minus 0.85. You understand? Beyond that also you can write down the values, but you see, the moment you are saying minus 1.50 is the maximum energy of electrons, that means all these electrons must have reached up to this much level. Because minus 1.50 कहाँ पे आएगा? Minus 1.50 यहाँ पे आएगा. But you see, the electrons are not allowed in the gap between the orbits. वो या तो 3 पे रह सकता है या 2 पे, इसके बीच के गैप में नहीं रह सकता. तो मे बी द इलेक्ट्रॉन हैज द टेंडेंसी टू रीच अप टू दैट लेवल, बट यू सी द इलेक्ट्रॉन्स मस्ट हैव मेड द ट्रांजिशंस लाइक दिस. कुछ इलेक्ट्रॉन्स 1 से 2 पे गए होंगे, कुछ इलेक्ट्रॉन्स 1 से 3 पे गए होंगे. अगर एब्जॉर्प्शन स्पेक्ट्रा की लाइंस हमसे पूछी जाती तो आंसर होता 2, क्योंकि एब्जॉर्प्शन लाइंस ज्यादा 2 बन सकती है. 1 से 2, 1 से 3, these are the 2 lines you can get. But once we are talking about the emission spectra, then you see the electrons which have reached up to this point, they can make a transition like this. After that, they can make a transition like this, and some of the electrons can directly jump to the bottom line. So you can have 3 lines. This is one line, this is another line, this is another line. So 3 lines will be there in the emission spectra. If you see the emission spectra, you will have at the most 3 lines. So maximum 3 lines. Possible in the emission spectra. Absorption में 2 lines और emission में 3 lines possible होंगी, which has been shown in the diagram. Now let us also make our concepts of energy values very much clear by another demonstrating example. Let's suppose you have another situation in which we say that if the potential energy of the ground state electrons if the potential energy of the ground state electrons is taken as 0, जो ग्राउंड स्टेट की पोटेंशियल एनर्जी है उसको हमने 0 लिया है, then find the total energy, of the first excited state. Understand, this is the kind of question we are posing. Now see, if you consider the situation, say this is n is equal to 1 and first excited state means n is equal to 2 you are having, isn't it? Ground state means n is equal to 1. This is first excited state, you can say. This is first excited state. This is ground state. If you talk about the kinetic energy at this place, then you see negative of kinetic energy is the total energy. So ग्राउंड स्टेट की काइनेटिक एनर्जी 13.6 इलेक्ट्रॉन वोल्ट होगी, और अगर फर्स्ट एक्साइटेड स्टेट की काइनेटिक एनर्जी देखी जाए तो दिस विल बी इक्वल टू 3.4 इलेक्ट्रॉन वोल्ट. ये वैल्यूज हमने कैसे लिखी है? ये वैल्यू सिंपली हमने टोटल एनर्जी की वैल्यू को नेगेटिव से मल्टीप्लाई करके लिख दिया है. नाउ इफ यू टॉक अबाउट द पोटेंशियल एनर्जी, देन यू नो दैट द पोटेंशियल एनर्जी इज डबल ऑफ टोटल एनर्जी. सो दिस वाज इक्वल टू -27.2 इलेक्ट्रॉन वोल्ट, और यहां की वैल्यू को अगर देखें आप तो ये -6.8 इलेक्ट्रॉन वोल्ट थी. दिस पोटेंशियल एनर्जी वैल्यूज दे आर डिपेंडेंट ऑन रेफरेंस, इजंट इट? इसमें हमने एक अजम्पशन ये लिया हुआ होता है कि जब इलेक्ट्रॉन फ्री हो जाएगा, दैट मीन्स n इज इक्वल टू इन्फिनिटी के लिए पोटेंशियल एनर्जी की वैल्यू 0 ली जाएगी, एंड बेस्ड ऑन दैट द वैल्यू ऑफ अदर levels they have the potential energy the way it has been written here. But so long as the kinetic energy is concept, so long as the kinetic energy is concerned, here kinetic energy is not dependent on any kind of reference. ये absolute values लिखी गई हैं, एंड जब आप इन दोनों को सम करते हैं तो टोटल एनर्जी की जो वैल्यू है वो इनकी सम है. तो इसका मतलब उसमें अगर पोटेंशियल एनर्जी रेफरेंस डिपेंडेंट है, सो नेचुरली द टोटल एनर्जी विल ऑल्सो बी डिपेंडेंट ऑन रेफरेंस, और इन दोनों को सम करके आप यहां पे लिखते हैं, isn't it? This is the kind of situation you have. Now if you read the question carefully, they are saying that this potential energy has been made 0. अगर आप इसको 0 करेंगे तो that is possible only if you have added 27.2 electron volt here. अगर आप यहां देखें तो लिख रहे हैं ये कि the potential energy of the ground state electrons is taken as 0. When is that possible? That is possible when you added 27.2 in this particular expression, and if you are adding potential energy value 27.2 for ground state, naturally you will have to add for the first excited state as well, isn't it? तो फर्स्ट एक्साइटेड स्टेट में अगर अब फिर हम टोटल एनर्जी की वैल्यू लेंगे तो जो भी अर्लियर वैल्यू थी उसमें 27.2 ऐड करना होगा आपको. अर्लियर वैल्यू वाज -3.4, सो टोटल एनर्जी of the first excited state, total energy of the first excited state is equal to -3.4 electron volt plus 27.2 electron volt. That way you can say -23.8 electron volt. This is the total energy you will be having for the first excited state. Remember that पोटेंशियल एनर्जी इज डिपेंडेंट ऑन रेफरेंस बट नॉट दी काइनेटिक एनर्जी. तो आपने पोटेंशियल एनर्जी में अगर चेंज किया तो सारे में वो चेंज होगा. काइनेटिक एनर्जी एज इट इज पुरानी वैल्यू रहेंगी, और उन सबका सम जो है दैट विल बी रिफ्लेक्टेड एज टोटल एनर्जी. सो नाउ दैट इज ऑल वी हैव इन अवर टुडेज फर्स्ट पार्ट ऑफ द डिस्कशन, दैट वाज बोर्स मॉडल ऑफ हाइड्रोजन एटम. सो बिफोर आई मूव अहेड, लेट मी समराइज व्हाट ऑल वी डिस्कस्ड इन अवर टुडेज लेक्चर. In our today's lecture of atoms, in the first part we first talked about the Thomson's model, Then we talked about the Rutherford's model. In which we talked about distance of closest approach. We talked about the relation between impact parameter and the angle of deflection. We also talked about the number of particles deflected at angle theta. Then mainly we talked about Bohr's model of hydrogen and like atoms, hydrogen and hydrogen like atom. In which we talked about the radius, speed, frequency, time period and energy of the nth orbit. Now, based on which we talked about hydrogen spectra, and explaining that was the Rydberg's formula. And then you had several solved examples explaining the underlying concepts. Understand? So this is all we had in our first part of the discussion of the chapter of atoms. In the next lecture, we will be talking about the mechanism in which X-rays are produced, and of course that will be on the higher energy level. So that is all we have in our today's discussion. Thank you.